Let's look at another type of indirect proof, which is a proof by contradiction. This is similar to a proof of the contrapositive, but it is slightly different. What we ultimately want to show whenever we do a proof by contradiction is that it must be the case that P implies Q, because if it's not, then there's something very strange. So we want to show that not P implies Q is somehow wrong. So logically, let's work out what it means to say that it's not the case that P implies Q. If it's not P implies Q, then that means that you can have P without guaranteeing that you have Q. So P can happen without Q happening. In other words, we can have P and not Q. Notice this phrase is not an implication. I'm not saying P implies not Q. All I'm saying is that you could have both P and not Q at the same time. So whenever you do a proof by contradiction, you essentially assume two things, both P and not Q, and then you show that something breaks down, so you reach some kind of contradiction. Okay, let's look at one of the most famous proofs of all time. This is that the square root of 2 is irrational. This is a very well-known proof by contradiction, and you've probably seen it before. So as is often the case with theorems, this is not phrased as an if-then statement. It's just a sentence. Square root of 2 is irrational, so we have to work out what the hypothesis and the conclusion are. So let's first identify P and Q, and then we will set up P and not Q. So we'll figure out what not Q would look like. Okay, so let's figure out our hypothesis and our conclusion. The conclusion is going to be that something is irrational. What? Well, the square root of 2. Let me call the square root of 2 x. So our hypothesis is that x squared is 2, and our conclusion is that x is irrational. Okay, so we're going to assume that x is a number whose square is 2 and prove that it must be irrational. Notice this is a very nice conclusion to negate. If Q is the idea that x is irrational, not Q is that x is rational. Okay, so to prove that the square root of 2 is irrational, we are going to assume that we have both P and not Q simultaneously. So we'll take P and not Q together. Again, because we're doing something strange here, we're bringing in the negation of the conclusion, we're going to tell the reader what we're doing. So whenever you're doing an indirect proof, please do state that it's an indirect proof. I like to say we proceed by contradiction or for the sake of contradiction, kind of a warm-up sentence. Okay, so for the sake of contradiction, suppose we have P and not Q. So suppose x squared equals 2, but x is rational. Since x is rational, there must be integers m and n out there so that x can be written as m divided by n. In other words, so that x is a ratio of integers. That's what it means to be rational. So assume there are two integers so that x is a ratio of those integers. It's a fact that any fraction can be reduced. So if you have 5 over 10, you could reduce that to 1/2. If you have 14 over 20, you could reduce it to 7/10. So let's go ahead and assume that the integers m and n that we've identified are giving us the reduced form of x. Moreover, we may assume that x is reduced by supposing that the greatest common divisor of m and n is 1. That's just a fancy way of saying that m and n don't have any factors in common besides the number 1. In other words, they're reduced. Okay, now let's use this representation of x. If x is m over n and x squared is 2, then we can say that 2 is m squared over n squared because that's what x squared would be. Now I'm going to bring that n squared over. So this implies that m squared equals 2 times n squared. Now look at what we have and think about the theorem that we just proved. This sentence suggests that m is an integer whose square is even. But we just proved that if a integer square is even, the original integer must be even. So m is an integer whose square is even. By the previous result, we know that m must be even. Notice I'm citing something that we just did. Anytime you can refer specifically to a previous theorem that supports your argument, do so, especially if it's a named result. So if it's a very famous theorem and it has someone's name on it, please cite it whenever you can. The previous result doesn't really have a name, but we just did it. So it's very specific for me to say by the previous result, m is even. So m equals 2k for some integer k. Now we have a nice representation for m, so let's use that. Let's substitute m equals 2k into our expression 2 equals m squared over n squared. If I square out that numerator m, I get 4k squared. Notice there's a 2 on both sides, so let me do some simplification. And we get n squared equals 2k squared. Once again, n is an integer whose square is even. So a second application of the previous theorem allows us to conclude that n is even. And now we've actually reached a contradiction. When we began and we picked m and n, we did it in such a way so that their greatest common divisor was 1. In other words, m divided by n was reduced. You couldn't simplify it any further. Yet, along the way, we've discovered that m is even, and now n is even, which means that their greatest common divisor can't be 1 because 2 is an even greater common divisor. So therefore, if m and n are both even, then our representation for x as m divided by n is not in reduced form, and this is a contradiction. Therefore, x cannot be written as a ratio of integers, so therefore, x is not a rational number. Okay, so this is a very famous proof by contradiction. Proofs by contradiction are actually pretty fun once you get the hang of them. For a lot of people, it's almost their go-to method to try to prove something is to set up this contradiction and then show that something is absurd. Sometimes it is the case that a proof by contradiction is absolutely the best method to proceed. If you want to show the square root of 2 is irrational, I think this is the most elegant way to do it. So I'm not trying to say with what I'm about to say that a proof by contradiction is a bad idea 100% of the time. However, as we go through the material and you look at proofs, whether it's something you're writing on your own or you're going over a proof that I do in lecture, always ask yourself, can I prove this directly? Because there's an argument to be made that a direct proof is better than an indirect proof, because a direct proof shows why the hypothesis leads to the conclusion. It's nice to say, if P then Q, because look at how P leads to Q. I think that's a very natural way to proceed. So a direct proof is a very beautiful thing when it can be done. Indirect proofs can actually be more fun, they can be very clever, and again, sometimes they really are the best method of proof. But when you do an indirect proof, you're kind of starting on the conclusion side, or you're working with a conclusion, and it's not quite as satisfying, in my personal opinion, as a direct proof. So don't get too addicted to indirect proofs, and do try to think, is it possible to show that the hypothesis leads directly to the conclusion? Just as I said a second ago when we did the indirect proof, here a proof by contradiction is a very natural way to take, because look at Q up here. Why is it good to have not Q instead of Q? It's good to have not Q because when we negated the conclusion, we gained a lot of power over the number x. If x is rational, then it's a ratio of integers and we have a representation for it. Irrational numbers are essentially defined as just not rational. So if we tried to stick with Q, our original conclusion, then we run into a problem of how do you express that a number is irrational? So how could I write down a good version of x using this fact that it's irrational? And that's just not so easy, because you can't like say it's a ratio of not integers or something like that. So rational numbers are easier to work with than irrational numbers. just like a second ago when we had the proof by contrapositive, I said one nice thing is it's better to square than to take the square root, right? So these are the kinds of uh, things that you can think about when you're trying to figure out if you should proceed directly or indirectly.